Hey guys, how are you all doing? It's Jalaj here again, back with another video from BHM at GCSE Chem. And today we're going to be doing C3.9 Bonding and Metals. I'm really sorry I couldn't make a video yesterday because nowadays, from now on I'm getting quite busy. It's like in August now I have mocks in September, so yeah, I am getting quite busy nowadays. So I can't guarantee daily uploads nowadays. From now on and until at least my mocks. I'll try my best to do daily uploads, but it might not always be possible because of me preparing for my mocks, and I just get really busy on certain days and some days, and basically that's the reason why I couldn't upload yesterday. And which does mean that we are going to finish later than what I said. I think it was 23rd or 24th October, which means we might finish later on. But I'll definitely try and finish the course as soon as possible. And today we're doing C3.9 Bonding and Metals, a really good section actually, not very hard. It's quite basic. And I feel in this section I'll be able to teach you much better because it's actually a section that it's very logical. It's not a section like the last section. If you saw the last video, C3.8, which was fullerenes and graphene, where you literally had to regurgitate pretty much most of it, if not all of it. But and also, sorry if you can hear any noise. It's really hot where I am, so I just wanted to turn the fan on. That's why. Sorry if you can hear any noise there. But the book I'm using is the AQA GCSE Chemistry Caboodle Revision Guide. I've shown you this before. I'll show you this in this video as well. I'll show it, and in the coming videos, in all the other videos, I'll show it as well. So and again, I haven't been able to update my website. Put the links for after C3.1. Really sorry about that. I'll try and I'll pretty much try and do it by today. I said I will do it by Sunday, but I'll try my best to put it all by. Do it all by today. Put the links to the website on my website for sections C3.2 up till C3.9, which is obviously today's video. But I'll try and do it all by today, so that it's fully updated. And if you're following the student book, it's pages 52 to 53. And so, as I said before, today we're doing C3.9 Bonding and Metals. So I think I don't have anything else to say other than obviously I'm back in the living room now. I'm making a video in the living room today. Or in the lounge you could say, but basically so let's start now. C3.9 Bonding and Metals. So the atoms in a metallic element, the atoms in a metallic element are all the same size. They form giant structures in which layers of atoms are arranged in regular patterns. So that basically describes how kind of metallic elements are arranged. All the atoms of metallic elements have the same size. That's very important, and they form giant structures. And they form giant structures basically in which layers of atoms are arranged in regular patterns. In the bonding in a metal, the structure of a metallic elements that there are basically they're giant structures basically, which have in which layers of atoms basically are arranged in regular patterns, which means the patterns are very regular. I'll show you what it looks like in a minute. In fact, I'll show you now. This is how this yellow, the circles, this is how metals, atoms of metallic elements are arranged. So I'll just read out what it says in the orange text beneath it. So the closely packed arrangement of copper atoms in copper metal. So this is showing copper, and you can see obviously the copper atoms in the copper metal are basically arranged. They're very closely packed. The atoms are very closely packed together in a regular pattern, and you could also see all the atoms are the same size, and they form giant structures, and basically everything that was here in which layers of atoms are arranged in a regular pattern. So now we have the first question of the section, and it says how are atoms arranged in a metal? Well, we've talked about that. Atoms in a metal, they have giant structures basically in which the layers are arranged in regular patterns, and basically the atoms in a metal are basically atoms of a metallic element are basically closely packed together. So that's all you have to say. So I'll just see what it says in the actual answers, so that I'm making sure that I am correct of what I'm saying. Yeah, so in a giant structure, as I said, you have to mention giant structure. They're arranged in a giant structure. They're closely packed together, the atoms, we said that. In layers, I said they were in layers as well. These closely packed atoms which are in layers with a regular pattern. Yeah, it says with a regular pattern. So I basically mentioned all of it in my answer. Basically all of it is mentioned. And so let's read on. It's quite a short section actually, this one, so it shouldn't take too long. So now we're looking at, so when metal atoms pack together, the electrons in the highest energy level, which are the outer electrons, delocalize and can move freely between the atoms. So so basically what it's saying that, metal atoms, metals have basically delocalized electrons, or they have their outer electrons. So outer electrons, which are electrons in the highest energy level, these basically electrons, they delocalize, which means they can freely move about between the atoms. That's very important, and that's actually the kind of reason why metals can actually conduct electricity, is because they do have delocalized electrons from their that come from the outer energy level, outer shell, you could say. So you say so then it says this produces a lattice of positive ions in a sea of moving electrons. So I understand this might not make sense at the moment, but basically what you have in a metal, you have positive ions and you have basically electrons from the highest energy level. So basically when metal atoms are packed together, so that when they're closely packed together, electrons in the highest energy level, or the outer electrons, they delocalize. Delocalize just means they're free to move about. And so what happens is, because obviously now the atoms have lost electrons, which have become, because obviously the electrons were first bound to the atoms, but now these electrons, remember, they are delocalized, they're free to move. So now that's why positive ions are formed, because obviously that metal atoms have lost electrons now to form positive ions, positive metal ions. And these basically, this produces a lattice of positive ions in a sea of moving electrons. You could say a sea of moving electrons, or you could say in a sea of delocalized electrons. They just mean the same thing, but that's why it says positive ions. That's why there's a lattice of positive ions. That's why positive ions are formed. It's because the electrons are delocalized. Because originally, in an atom, you'd have all the electrons which are around the atom, right? And then, so you'd have all the electrons around the atom. But then when the electrons delocalize, which means when they move out, when they're free from the atom, they are free to move about. Because when they're kind of around the atom, they're kind of bound to the atom. So like they're kind of stuck. I don't know, stuck's maybe not a good word to use, but basically they're on the atom. Basically they're moving around the atom. But when they're delocalized, they're free to move, so they're now no longer on the atom. So that's why the atom loses an electron or loses electrons, and basically the lattice of positive ions are formed. Basically that's how the lattice of positive ions are formed, because of the electrons being lost. And so basically this produces a lattice of positive ions in a sea of moving electrons or delocalized electrons. So hopefully that makes sense. And now the delocalized electrons strongly attract the positive ions and hold the giant structure together. So this is how the kind of giant metallic structure is held together, otherwise everything would fall apart. It's because of this electrostatic attraction. We call it electrostatic attraction between the positively charged ions. You could say the positive ions. It don't say positively charged. I think they say positive ions because they normally say positive ions. I don't think you're going to lose a mark for saying if you said positively charged ions. But in this book it says positive ions. When you're dealing with bonding in metals, I'd say the electrostatic attraction between the positive ions and the delocalized electrons. And this strong attraction holds the giant structure together. This is what holds the giant metal structure, lattice structure together, basically. And 1 minute. So this is just a diagram here. You can see these are showing the outer electrons. Hopefully you can see them in black dots in the atom. But then what happens is these electrons are now in this diagram. They're free to move. Basically that's how it all works, because the electrostatic attraction between the positive ions and the delocalized electrons, or sea of moving electrons, or sea of delocalized electrons. This electrostatic attraction is what holds the giant structure together. So hopefully you can see it. hopefully I saw it clearly. You could obviously see a positive charge here, and then you can see hopefully a black dot there on the outer. That shows the outer electrons. That's just for this atom, but basically they're for all the other ones as well. And then obviously these electrons are then free to move or delocalized, or C of delocalized electrons, or basically So here it just says, here obviously says metal atom's outer electron, or you can even say valence electron. And then in the next image it obviously showed the C of delocalized electrons, because now they're free to move. So hopefully that makes sense. Now a metal consists of, so there's just some orange text as well, I'll read that. A metal consists of positively charged metal ions surrounded by a sea of delocalized electrons. The diagrams show us a model of metallic bonding. So this is just a representation of basically how metallic bonding, is to represent metallic bonding, show how it kind of works. It's basically that if you had to define metallic bonding in the exam, you just say it's the electrostatic attraction between the positive ions and the sea of delocalized electrons. So hopefully that makes sense. And then here's a question again. What forces hold the metal atoms? So here's the second question. What forces hold metal atoms in place in their giant structure? So that's obviously the electrostatic attraction, the strong electrostatic, the electrostatic attraction between the positive ions and the delocalized sea of delocalized electrons. So there's these strong forces, strong electrostatic forces of attraction. That's the answer. That should be the answer to the question. I'm pretty sure. Yeah, the electrostatic forces between the positive, you can say positive metal ions as well, between the positive, in brackets it says metal. I think it's good to actually specify metal. I didn't say metal, but because I knew what I meant, but you probably knew what I meant as well, because you probably know what I meant, because we're talking about metals here. But it's good to say the electrostatic forces between the positive metal ions, although it says metal in brackets. Whenever something is brackets, it's not very important, but it's still good to mention. So the electrostatic forces of attraction between, or forces between the positive metal ions and the delocalized electrons is the answer. So that's basically what I said. And here's a nice study tip actually: make a model of a metal structure using marbles or polystyrene balls. Right, you can use marbles and polystyrene balls. I think that's just a good way of kind of visualizing it, to kind of understand how the structure works. But if you understand it, you don't really need to do that. But that's just if you need more help understanding this topic. I think sometimes visual representations using real life examples, using real life objects are good. I find them quite helpful actually for some of my work. Especially because obviously chemistry is a very molecular subject. I think because you can't see electrons, you can't see atoms. They're really, really small things. That's why it's good to have these kind of visual representations. So I do quite like this tip. So make a model of a metal structure using marbles. So using marbles or polystyrene balls. So you can do that. That would be a nice way to kind of demonstrate the metallic bonding. That would be a nice way to demonstrate it. Yeah. And understand it as well. So the keywords of this section are, or the key word actually, there's only one keyword. Delocalized electrons is the only keyword here. And just before we finish, we'll go over the key points quickly. So the atoms in metals. Let me start again. Key points. The atoms in metals. Let me just say that again. The atoms in metals are closely packed together and arranged in regular layers. Yeah, we've been through that. We've been through the fact that the atoms of the metals, they're closely packed together, or you could say tightly packed together. I think closely packed together is better because that's what's in the book, and they're also arranged in regular layers. We know that. We've just been through that. And then it just says here also that you can think of metallic bonding as positively charged metal ions, which are held together by electrons from the outermost shell of each metal atom. So basically, metallic bonding is basically where the positively charged metal ions are held together by electrons. Yeah, basically, you can think of it as basically the electrostatic attraction between the positively charged metal ions. Here it says positively charged, so I think you can say positively charged metal ions. So yeah, it's basically the kind of, you can think of metallic bonding as the positively charged metal ions, which are held together by the kind of outermost electrons of, or outermost kind of shell of electrons from the outermost shell each metal atom, basically, because the outermost electrons of the metal atoms are what holds, they hold basically the positive they hold the positively charged ions together. Basically, they make sure that they hold the giant structure together. That's the important part. Yeah, I think that's it. It says, wait 1 minute, have I missed something? I don't think I have. Yeah, that's what hold the giant metallic structure together, you can say. Yeah, it's these electrons which come from the outer shells of the atoms, of the metal atoms, that hold the positive ions together. And it's this electrostatic attraction between the positively charged metal ions and the sea of delocalized electrons, or you could just say delocalized electrons, that basically that is what metallic bonding is. It's this electrostatic attraction. And then the last key point is that these delocalized electrons are free to move throughout the giant metallic lattice. Yeah, you could say giant metallic structure, or you could say giant metallic lattice. It's these delocalized electrons that are free to move throughout the giant metallic lattice or giant metallic structure. So basically, just saying these electrons are basically free to move. They can move about, in the metal structure throughout the giant metallic structure. So, or giant metallic lattice. So that's the end of the section, guys. Tomorrow we'll be going through C3.10. If I'm not busy, I don't think I will tomorrow, but you never know. But yeah, tomorrow we're most likely going to go through C3.10, giant metallic structures. And so it's all about, here is also about alloys and stuff. So we're going to see that in the next section. And I really hope this video was helpful, guys. And also, I don't know why I have a habit of scratching my head a lot, but there you go. I said this video wouldn't be too long, but it's already been past 17 minutes. So yeah, I do ramble on quite a bit, but I do talk a lot. But there you go. So yeah, that's the end of the section, guys. C3.9, which is called the bonding. C3.9, which is bonding in metals. And so hopefully this video was helpful. Make sure to share, like, and subscribe. Turn the notifications on. Turn the notification bell on if you haven't already, so you're notified and updated when I upload new videos that you can watch. I'll try and get the links to C3.2 till C3.9 up on my website by today. Hopefully, I'm really going to try and do it, guys. I should have done it before, but I was really busy as well, doing other stuff, as I've told you about my mocks that are happening in September. The end of September, which you might think is quite a long time, but still need to revise quite a lot for that. For them. So I think I'm gonna go now. I think I'm gonna go now, guys. I'll see you tomorrow for C3.10, which is all about giant metallic structures. Until then, see you guys, and thank you very much.